In this section, we will talk about liquids and solids. Let's talk about states of matter. Comparison of gases, liquids, and solids. Gases are compressible fluids. Their molecules are widely separated with no volume or shape. Here's a picture showing you that a gas typically fills up the entire container and have lots of space between molecules. Liquids are relatively incompressible fluids. Their molecules are more tightly packed and touching with volume but no shape. Solids are nearly incompressible and rigid. Their molecules or ions are in close contact and do not move with volume and shape. A change of state or phase transition is a change of the substance from one state to another. Liquids freeze or undergo crystallization to form solids. Solids melt or undergo fusion to form liquids. Gases condense to be liquids, or liquids boil or vaporize to be gases. Gases can go straight to being solids under the term of condensation or deposition, and solids can go straight to being gases by sublimation. The energy associated with change in states is equal for both directions, but opposite in sign, meaning exothermic or endothermic. The processes of gases going to be a liquid, or liquids going to be a solid, or gases going straight to be a solid, or exothermic processes, meaning that they release heat. Going to be a solid, from a solid going to be a gas, or a solid going to be a liquid, or a liquid going to a gas, those are endothermic processes, meaning it absorbs heat. Liquids are continuously vaporizing even if they're not at their boiling point. If a liquid is in a closed vessel with space above it, a partial pressure of the vapor state builds up in that space. The vapor pressure of a liquid is the partial pressure of the vapor over the liquid, measured at equilibrium at a given temperature. The more gas molecules, in other words vapor, the higher the vapor pressure. Those gas molecules are what's creating that vapor, that pressure. The vapor pressure of a liquid depends on its temperature. As you can see by the graph, as the temperature increases, the kinetic energy of the molecular motion becomes greater and the vapor pressure increases. More energy is available to convert the liquid molecules to a gas. Hence, more gas molecules are there and a higher vapor pressure. So the more gas molecules, the higher the vapor pressure. The more gas there to add to that pressure. So you can see as the temperature increases, the vapor pressure is increasing as well. Liquids with relatively high vapor pressures at normal temperatures are said to be volatile. The higher the vapor pressure, the easier it goes from a liquid to a gas. Example, acetone has a high vapor pressure. It is very volatile. If I put a drop of acetone on a table, it's going to evaporate pretty quickly. Has a high vapor pressure, very volatile. If I put a drop of water on the table, it's going to be there a while, but eventually it's going to change into a gas. It's not as volatile and doesn't have as high a vapor pressure. Boiling point. The temperature at which the vapor pressure of a liquid equals the pressure exerted on the liquid is called the boiling point. As the temperature of a liquid increases, the vapor pressure increases because more gas molecules are being formed until it reaches atmospheric pressure. When it reaches that atmospheric pressure, that's when it begins to boil. At this point, you have stable bubbles of vapor coming through the liquid. Those bubbles coming through the liquid is that same species. It's basically going from a liquid to a gas, and it's getting to the surface of the liquid and escaping. This is called boiling. The normal boiling point is the boiling point at 1 atmosphere, or 760 millimeters of mercury. Because atmospheric pressure varies with altitude and weather conditions, the boiling point of a liquid does as well. For example, we know the boiling point of water at 1 atmosphere is 100 degrees C, but the boiling point of water is about 71 degrees C on Mount Everest at 8,850 meters of elevation. It has approximately 0.33 atmospheres. So as the atmospheric pressure decreases, your boiling point is going to decrease as well. We noted that vapor pressure was a function of temperature. It has been demonstrated that the logarithm of the vapor pressure of a liquid varies linear with the absolute temperature in the Kelvin scale. So consequently, the vapor pressure of a liquid at two different temperatures is described by the following equation, where Ln is your natural log, P2 is your pressure or vapor pressure over the vapor pressure at one condition versus the other. Delta H is your heat of vaporization. R is the gas constant. 1 over temperature 1 minus 1 over temperature 2. This equation allows you to determine the vapor pressure of a system at any temperature if you know the vapor pressure at the normal boiling point. So if you know one condition, you can find the vapor pressure at a different condition. Let's look at an example. Carbon disulfide has a normal boiling point of 46 degrees C. Vapor pressure 760 millimeters of mercury. It has a heat of vaporization of 26.8 kilojoules per mole. We want to know what is the vapor pressure of carbon disulfide at 35 degrees C. First, we know we got to do this at Kelvin, so we change the temperatures. 46 degrees C is 319 Kelvin, 35 degrees C is 308 Kelvin. Well, substitute into the Clausius-Clapeyron equation, which is the equation we just talked about in the previous slide, we can attain the following. We got natural log of P2 over P1, which we're calling your 760 millimeters of mercury, is equal to your delta H, which is 26.8 times 10 to the third joules per mole. Converted it to kilojoules to joules. So I can cancel that with the R I used, which is 8.31 joules per mole Kelvin. Time 1 over T1, which is 319 Kelvin, minus 1 over T2, which is the temperature we're trying to figure out the vapor pressure of. Notice units cancel, joules cancel, moles cancel, as well as the kelvins. I get my mathematical numbers. I get my 3225 time my negative 1.12 times 10 to the negative fourth. Those kelvins cancel. I already canceled it above, but here they are, they cancel in here, which gets me mathematically a negative 0.361. Well, we got the natural log of P2 over 760, so to get rid of this natural log, we're going to have to take the anti-log of both sides. Taking the anti-log, we get now P2 over 760 millimeters of mercury. We lost the natural log on the left side. Now we have the anti-log of the other side. Anti-log is basically telling us we're doing an e to the x. That's basically your second function on your calculator for your natural log. If you have just hit your second function and your natural log button above that probably says e to the x, or you may have a table if you have the expensive calculator. But you're trying to do an e to the x function for negative 0.361, which tells me I multiply both sides by the 760 to get south of the P2, which tells me my pressure is 530 millimeters of mercury, which makes sense because if the temperature decrease, then the vapor pressure should decrease as well. The temperature at which pure liquid changes to a crystalline solid or freezes is called the freezing point. The melting point is identical to the freezing point. It's the same degrees. Okay, the freezing point and melting point is just the difference of going in one direction versus the other, but it occurs at the same point. And is defined as the temperature at which a solid becomes a liquid. So if you got a solid going to a liquid, which is melting, there's a certain delta H associated with that. And it's going to be a positive value because it's an endothermic process. It's absorbing heat. At that same temperature, liquid's going to go to a solid, which is freezing. That's the same delta H, except it's a negative because we're trying to tell you that it's an exothermic process. It's releasing heat for that to happen. Unlike boiling points, melting points are not affected significantly by pressure changes. However, large pressure changes may have some effect. To melt a pure substance at its melting point requires an extra boost of energy to overcome some lattice energies. The heat needed to melt 1 mole of a pure substance is called the heat of fusion, or delta H subscript fuse. For ice, the heat of fusion is 6.01 kilojoules per mole. So if we're going from a water solid to a water liquid, the heat of fusion is 6.01 kilojoules. The opposite process of going from a liquid to a solid, okay, taking a liquid and freezing it, is called the delta H of crystallization, which is the same value, 6.01 kilojoules, except it has a negative sign to indicate that it's an exothermic process. To boil a pure substance at its boiling point requires an extra boost of energy to overcome intermolecular forces. The heat needed to boil 1 mole of a pure substance is called the heat of vaporization and denoted delta H vapor. For liquid water, the heat of vaporization is 40.66 kilojoules per mole. So if we're going from a liquid to a gas, okay, boiling, the heat of vaporization is 40.66, and that's an endothermic process. The opposite way, water gas going to be a liquid, it's called the delta H of condensation, same value, 40.66, but it has a negative sign because this is stating that this is an exothermic process. That's the amount of heat that has to be released for the process to happen. This is a heating curve for water. Notice we start down in ice, and the temperature, as we add in heat to this, the temperature is increasing, which makes sense. Then when it reaches 0 degrees C, that is the freezing point of water, notice that the line stays straight. Even though we're adding heat, the temperature doesn't change. That's because it's using that heat to change states, to go from a solid to a liquid. Then after all the ice becomes water, liquid, then the heat starts increasing again and the temperature starts to rise. Once it reaches the boiling point again, the temperature stays level again until all that liquid changes into a gas. If you were to stick a thermometer in your water as it was boiling on the stove, you would notice that once it reaches the boiling point, 100 degrees C, the temperature does not change until all that liquid was to change into a gas, and then the temperature will start rising again once it hits steam, as we see here. So, the temperature does not change while it's changing states. Heat is used to overcome forces of attraction. So that amount of heat to go from a solid to a liquid is 6.01 kilojoules of energy. Then it goes up, and then when it goes from a liquid to a gas, it needs 40.66 kilojoules of energy to change from all being a liquid to a gas. And then the opposite process coming down. A phase diagram is a graphical way to summarize the conditions under which the different states of a substance are stable for different temperatures and pressures. The diagram is divided into 3 areas representing each state of a substance. The curve separating each area represents the boundaries of phase changes. Below is a typical phase diagram. It consists of 3 curves that divide the diagram into regions: solid, liquid, and gas. On the left side is my solid region, my middle is the liquid, and on the right is my gas. Basically, at any pressure and temperature, I can figure out if it's a solid or liquid or gas by using this phase diagram. The curve AB divides the solid region from the liquid region and represents the condition under which the solid and liquid are in equilibrium. So, anywhere along this line, I will have my conditions of where we go from a solid to a liquid. That's the temperature and pressure. At any point on this line, I can determine that freezing point, melting point. Notice that there's a slight tilt in this for that, saying that it's somewhat related, affected by pressure. Usually the melting point is only slightly affected by pressure. For this reason, the melting point curve AB is nearly vertical, so it's only slightly affected by it. Contrary to your gas-liquid phase, you can see is in a line that's affected dramatically by pressure. If a liquid is more dense than a solid, and the major example of that would be water, the curve leans slightly to the left. It always points to the less dense state. So it's pointing to the less dense, meaning that the solid is less dense than the liquid. That's why ice cubes float in water. This is causing the melting point to decrease with pressure. It's only very slightly affected. Notice that the line is nearly straight, so it affects it slightly. However, if a liquid is less dense than a solid, the curve leans slightly to the right toward the less dense liquid, causing the melting point to increase with pressure, only slightly again. Notice most solids are more dense than liquids. Okay, water is one of those exceptions. The curve AC, which divides the liquid region from the gaseous region, represents the boiling points of the liquid at various pressures. Note that pressure has a major effect on the curve in the boiling point. Temperature and pressures along this line give me the liquid-gas equilibrium, where we're talking about boiling to a gas or condensing back to a liquid. Those are the temperature pressure ranges. Curve AD, which divides the solid region from the gaseous region, represents the vapor pressure of the solid at various temperatures. An example of a solid that goes directly to a gas is dry ice. That's why it's used in packing to keep things cold, because there's no moisture accumulated from it going from a solid to a gas. And these are the temperature and pressures along that line where you can determine that sublimation and deposition temperature and pressures. The curves intersect at point A, which is called the triple point, which is the temperature and pressure which all three phases, your solid, your liquid, and your gas, of a substance exist in equilibrium. Example, water occurs at 273.15 Kelvin and 4.58 torr. That's the spot where the temperature and pressure where we have all three phases. That's called the triple point. The temperature above which the liquid state of a substance no longer exists regardless of the pressure is called your critical temperature. The vapor pressure at the critical temperature is called the critical pressure. Note that the curve AC ends at the critical point C. Their line stops. Okay, it's no longer a liquid there. No liquefaction is observed above the critical temperature. When the pressure of the gas above the critical temperature is increased beyond the critical pressure, we have what is called a supercritical fluid, which has totally different properties than the liquid before. So above that critical temperature and critical pressure, we have a supercritical fluid. In general, properties like boiling point, melting point, viscosity, vapor pressure, and surface tension depend on the strength of the attractive forces among the molecules. The stronger their attractive forces, the higher the boiling point. Viscosity and surface tension of the liquid as well as higher. The higher the melting point of the solid, and the lower the vapor pressure of the liquid. Molecules gain more freedom of movement as a solid melts or as a liquid vaporizes. The amount of energy that they need to overcome the forces of attraction among them increases the stronger the forces are. So the stronger the forces, the more energy is needed to overcome them. Surface tension is the energy required to increase the surface area of a liquid by a unit amount. A molecule within a liquid is pulled in all directions, whereas a molecule on the surface is only pulled to the interior. Here's a picture. Here's a molecule in the middle, so it's pulled in all directions by the other solvent molecules. On the surface, it's pulled in all directions below, but nothing's pulling from the top. As a result, there is a tendency for the surface area of the liquid to be minimized. To increase the surface area of the liquid requires movement of molecules within the interior, whereas they experience stronger attractions to the surface. This requires energy. The stronger the intermolecular attractive forces between molecules, the higher the surface tension. So the stronger their attraction is between the molecules, the more pull it's going to have inward, the higher the surface tension. Viscosity is the resistance to flow exhibited by all liquids and gases. Viscosity can be illustrated by measuring the time required for a steel ball to fall through a column of a liquid. The less viscous a solution is, the faster the ball will drop. The more viscous it is, the slower it will drop. Even without such measurements, you know that syrup has a greater viscosity than water. It's thicker the fluid, the more resistance to flow. The stronger the intermolecular attractive forces are among the molecules of a gas or liquid, the more resistance they will be to flow, the higher the viscosity. So the stronger the forces are of attraction, the higher the viscosity. The harder, the more it resists to flow. You can lower the viscosity of a substance by increasing the temperature, giving the system more energy to overcome the attractive forces, thereby increasing flow. By putting energy into the system in the form of temperature, you can overcome those attractions and increase the flow. The attractive forces between two molecules can be classified into two major types. Van der Waals forces, which are the weak attractive forces in large number of substances, all covalent bonded, and hydrogen bonding interactions, which occurs in substances containing hydrogen atoms bonded to certain very electronegative atoms, oxygen, nitrogen, and fluorine. Van der Waals forces can be further classified into, number one, London dispersion forces, which occur between any pair of molecules, so all molecules have this. Dipole-induced dipole interactions occur between a nonpolar molecule and a polar molecule. And dipole-dipole interactions, which occurs between two polar molecules. London forces refer to the force of attraction that exists between any pair of molecules and is predominant interaction among most molecules. It is due to temporary molecular polarizations, which occurs because electrons are always moving, causing a distortion of the electron cloud surrounding a molecule. The larger the molecule, the more frequently the polarization occurs. Therefore, we expect attractions to be stronger among larger molecules. This means London forces increase with molecular weight. The larger a molecule, the more easily the electron cloud can be distorted. Let's look at nitrogen and oxygen as pure substances. Both are nonpolar molecules that only have London dispersive forces of attraction. Since they only have London forces, the molecule with the larger molar mass will have more polarization and a higher boiling point, a higher viscosity, a higher surface tension, as well as a lower vapor pressure. So, the molar mass of nitrogen is 28, molar mass of oxygen is 32. Since oxygen has a higher molar mass, and all we have is London dispersive forces of attraction to overcome, we expect it to have a higher boiling point than nitrogen. Boiling point of nitrogen is a negative 196 degrees C, oxygen a negative 183 degrees C. So oxygen has a higher boiling point than nitrogen. Dipole-dipole interactions refers to the force of attraction that exists between polar molecules. The dipole-dipole interaction is an attractive intermolecular force resulting from the tendency of polar molecules to align themselves positive end to negative end. There is a higher electron density in the chlorine end of the polar molecule. We say that this end is partially negative. The hydrogen end of the polar molecule is partially positive and is attracted to the partially negative end of a nearby HCl molecule, which is a dipole-dipole interaction. It is the attraction of the negative end to the positive end from one molecule to the other molecule. Let's look at N2, NO, and O2 pure substances. We have the molar mass of N2 is 28, molar mass of O2 is 32, and NO is right in between. Both N2 and O2, as we know, are nonpolar molecules that only have London dispersion forces of attraction. However, NO is a polar molecule, which also has dipole-dipole interactions in addition to London forces to overcome. This will affect the boiling point, viscosity, and surface tension and vapor pressure. Since you have dipole-dipole interactions to overcome, even though the molar mass is right between these two, the boiling point is going to be affected, as well as viscosity and surface tension. All those will be higher, and the vapor pressure will be lower. The Boiling point of NO would be the highest among these substances because of the additional dipole-dipole interactions in the polar molecule. Nitrogen at negative 196 degrees C, oxygen at negative 183, and you can see NO is higher than both of those at a negative 152 degrees C. Dipole-induced dipole interactions refer to the force of attraction that exists between a polar molecule and a nonpolar molecule. When a nonpolar molecule comes close to a positive end of a polar molecule, its electrons will be attracted toward the polar molecule, causing temporary or induced polarization. Similarly, when a molecule comes close to a negative end of a polar molecule, its electrons will be repelled again, causing temporary induced polarization again. Hydrogen bonding is a force that exists between a hydrogen atom covalently bonded to a very electronegative atom, meaning oxygen, nitrogen, or fluorine. To exhibit hydrogen bonding, one of the following three structures must be present. Must have hydrogen attached to nitrogen, hydrogen attached to oxygen, or hydrogen attached to fluorine. Only nitrogen, oxygen, and fluorine are electronegative enough to leave the hydrogen nucleus almost stripped bare of electrons, making it strongly attracted to a lone pair of a highly electronegative atom such as oxygen, nitrogen, and fluorine in a nearby molecule. The hydrogen atoms in water are bonded to a highly electronegative oxygen atom. Okay, we see this hydrogen. That oxygen is stripping an electron because it's very electronegative. Because hydrogen is almost stripped bare of electrons, it is strongly attracted to the lone pair of the oxygen atom in a nearby water molecule. That attraction between that oxygen and that hydrogen is very strong, which is going to increase the boiling point, etc., for the substance. Hydrogen bond interaction is so strong that the dipole-dipole interaction, and even for small molecules, is stronger than London forces. Hydrogen bonding accounts for the unusually high boiling point of water. Water molecules are small and a liquid at room temperature. Substances made of molecules of comparable size are gaseous at room temperature. Oxygen is a gas at room temperature, while water is a liquid, even though water molecules are smaller than oxygen molecules. Water is a polar molecule and capable of extensive hydrogen bonding, thereby raising its boiling point considerably. Molecules exhibiting hydrogen bonding have abnormally high boiling points compared to molecules with similar van der Waals forces. Which of the following are capable of exhibiting hydrogen bonding? Remember, that is with hydrogen attached to fluorine, oxygen, and nitrogen, but they have to be in the Lewis structure that way. So looking at these, which one can exhibit that? Well, HF can. Okay, that fits the definition well. You got OH and fits the definition, as well as the OH over here. N2 naturally is not going to. HI is not going to. CH4 doesn't work. H2S doesn't fit those definitions. Now you may look at this one and say that looks like it fits the definition. It has hydrogens and oxygen, but they have to be attached. So the Lewis structure, if you were to look at this, you're going to have that oxygen and two carbons attached to it with your three hydrogens around the carbon. Okay, so the oxygen is not attached to the hydrogen, therefore that's not hydrogen bonding either. Within the Lewis structure of a molecule, hydrogen must be attached to oxygen, nitrogen, or fluorine for hydrogen bonding to occur. Let's look at water, H2S, H2SE, and H2TE as pure substances. If you draw the Lewis structure and examine the Vesper geometry of these molecules, you would determine that all of these molecules are polar with the same bent geometry. Okay, so we're dealing with a polar molecule in all four cases. This means that all the molecules have London dispersion and dipole-dipole interactions. Since they're all polar molecules, their London dispersion forces will dictate their boiling point, which will vary based on their molar mass. The larger molar mass, the stronger the London forces. So you have water at 18.02, H2S 34.08, then 80.98, and 129.63. Since they're all very similar, All polar molecules, you expect the one with the larger molar mass to have the higher boiling point. Based on molar mass, we look at our boiling points. We see that we have for H2Te, we have a -2, H2Se, -41.3, H2S, -60.33. Notice I didn't put one for the boiling point of H2O yet. If we were to extrapolate the boiling point of water based on the other actual boiling points, the boiling point of water should be at -68 degrees C. That would fall in line with the molar masses, etc. However, we all know that H2O does not boil at a -68 degrees C. Well, so what's going on here? Why is this smaller molecule different than the rest? Well, it goes back to that very strong hydrogen bonding to overcome. Its boiling point is actually extremely high, 100 degrees C, as compared to the other substances, despite its low molar mass. That hydrogen bonding is the key. That is a stronger bonding that takes more energy to overcome, therefore it changes its boiling point dramatically. Due to hydrogen bonding, H2O is at 100 degrees C. For which of the following pairs of molecules do we expect London dispersion forces, dipole-dipole, dipole-induced, and hydrogen bonding? Well, first you must realize through Lewis structures and VSEPR theory that CO2, CH4 are nonpolar, while water, HCl, and NH3 are polar. So we know from Lewis dot structures and VSEPR theory that CH4 is nonpolar. CH4 is nonpolar. Water is polar. Water is polar. Water is polar. CO2 is nonpolar. NH3 is polar. NH3 is polar. HCl is polar. And HCl is polar. So if we look at these species and we talk about London dispersion forces, we know that all species have that. So we would say that for London forces, all of them have London forces. Next, we're talking about dipole-dipole. To be dipole-dipole, you have to have polar molecules involved. Okay, a polar molecule and a polar molecule. So for this to occur, I need a polar and a polar molecule. So in that instance, we would say that water and water will be dipole-dipole, ammonia-ammonia, and HCl and HCl. For dipole-induced, we know that for that to occur, we need a polar molecule and a nonpolar molecule. So we're looking for an arrangement that has a polar molecule and a nonpolar molecule. Well, looking at that, there's only one, which would be your water and CO2. And the last one is hydrogen bonding. For hydrogen bonding, we know you'd have to have oxygen and a hydrogen, a nitrogen, or a fluorine involved in the Lewis structure. Looking at that, we know that we have hydrogen bonding occurring in our water-water. We also have that occurring in our ammonia-ammonia. Let's see if we can figure out which species has the higher boiling point between carbon disulfide and carbon tetrachloride. Well, to do this, we need to draw the Lewis structure and examine the VSEPR geometry of these molecules. If you were to do that, you would determine that both of these molecules are nonpolar, with CS2 having a linear geometry and CCl4 having a tetrahedral geometry. I suggest you draw these structures and make sure you can do that. Since they're both nonpolar molecules, the deciding factor is going to be molar mass. They only have London dispersion forces of attraction, which means the molecule with the larger molar mass, in this case carbon tetrachloride, will have more polarization and a higher boiling point. So the species with the higher boiling point in this case would be your CCl4. Let's try a different one. Which species has the higher boiling point? H2O or CO? Well, if you draw the Lewis structures and examine the VSEPR theory, and once again I suggest you do that, You would determine that water is a polar molecule with a bent geometry, and carbon monoxide is a polar molecule with a linear geometry. Since they're both polar molecules, you would think then that it's going to be the one with the higher molar mass. However, there's one thing we're forgetting. H2O has another type of intermolecular force we've got to worry about, which is hydrogen bonding. Since both are polar molecules, they have London dispersion and dipole interactions. Usually in this instance, the species with the larger molar mass would have the stronger London forces and higher boiling point. However, H2O also has hydrogen bonding, causing that boiling point to be much higher despite the lower molar mass. In summary, intermolecular forces play a large role in many of the physical properties of liquids and gases. These include vapor pressure. We know as the intermolecular forces increase, your vapor pressure would decrease. Since it's harder to overcome and cause a liquid to turn into a gas, you're going to have less gas there, which means the vapor pressure is going to be less, so the vapor pressure decreases. Boiling point. As the intermolecular forces increase, your boiling point increases. If you have strong intermolecular forces, it's going to take more energy to overcome that, so your boiling point is going to be higher. Surface tension. As intermolecular forces increases, as you got stronger pull on those molecules against themselves, that surface tension is going to increase. Viscosity. As the intermolecular forces increase, they have stronger attractions to each other. They're harder. It's going to resist flow more. That means your viscosity will decrease. The regular arrangement of particles in a crystalline solid leads to the minimization of total potential energy of interactions of particles in the most stable arrangement. Crystalline structure is said to have a long-range order. The overall structure can be thought of in terms of a repeating pattern called a unit cell. The unit cells making up the solid are in close contact and in fixed positions. Solids are characterized by the type of force holding the structure units together. In some cases, these forces are intermolecular, but in others, there are chemical bonds, metallic, ionic, or covalent. Properties of crystals depend on the type of particles in the lattice. Crystals can be classified as ionic, molecular, or atomic. Ionic crystals tend to have very high melting points due to strong attractions among ions. They are brittle due to the strong repulsions that result when ions of like charges are momentarily brought closer together as ions are slightly displaced from their locations when the crystal is, say, hit by a hammer. Molecular crystals tend to have low melting or sublimation points. The attractive forces among the molecules are relatively weak, mainly van der Waals forces. Atomic crystals can be classified as non-bonding, metallic, or covalent network. Non-bonding atomic crystals are formed when noble gases are frozen to very low temperatures. These atoms are held together by very weak London dispersion forces. Metallic crystals are made up of atoms of metallic elements. If more than one element is present, the solid is a solution and is called an alloy. A strong metallic bond is the reason metals have high melting points and boiling points. Most metals are solids at room temperature. Because metal atoms can readily slip and roll over each other without breaking the metallic bond, metals are malleable and ductile. Covalent network crystals can be thought of as one giant molecule. The atoms are held together by very strong covalent bonds. Thus, a network covalent crystal like diamond has a very high melting point and is among the hardest material known. Many physical properties of a solid can be attributed to its structure and forces of attraction called crystal lattice energy or ion-ion intermolecular forces. For a solid to melt, the forces holding the structural units together must be overcome. For a molecular solid, these are weak intermolecular attractions. Thus, molecular solids tend to have low melting points, below 300 degrees C. For ionic solids and covalent network solids to melt, chemical bonds must be broken. For that reason, their melting points are relatively high. Note for ionic solids, melting points increase with the strength of the ionic bond while solubility decreases. Ionic bonds are stronger when the magnitude of charge is high. The higher the charge, the stronger the attraction, the more energy needed to overcome attraction. Therefore, the melting point increases and the solubility decreases. The ions are small, higher charge density. The smaller the radius, the closer the opposite charges and larger attraction. The more energy needed to overcome attraction, therefore, the melting point increases and solubility decreases. Summary. The attractive forces crystal lattice energy between a pair of oppositely charged ions increases, meaning a stronger bond, as the charges of the ions increases and as the ionic size decreases, hence higher melting point and lower solubility. Which of the following has a higher melting point and lower solubility? Magnesium oxide versus sodium chloride. Well, since magnesium oxide involves higher charges, +2, -2, than sodium chloride, which is +1, -1, magnesium oxide will have higher melting point and lower solubility. It will have a stronger bond, therefore take more energy to overcome. How about calcium bromide versus calcium chloride? Well, since both species have the same charges, +2, -1, the size of the ions, the anions in this case, will affect the properties. Calcium chloride has the smaller anion, therefore it will have a stronger attraction to calcium and have a higher melting point and lower solubility. Homework 69.